Okay, we're going to continue with our trig derivative unit, and we finished off limits, so now today we're going to use those limit concepts and apply them to finding the derivatives. So just like we did in the first thing we want to figure out limit section earlier in the year, remember once we understood the limits of sine x, we use this limit formula that I've got in the yellow box, or the limit of sine x, help us figure out how derivatives work. We'll figure out. So we can do the same thing. We can apply this limit formula to any sort of trig function. So our first step. So when we did this before, if I gave you a function something like y equals x squared, remember we would find the limit as h approaches 0. We'd put in x plus h squared minus x squared all divided by h, and then we'd FOIL it out and simplify, and we'd see that we'd end up getting something like 2xh plus h squared or something like that, and then when we divided by h's, all that was left over was 2x, and we saw that that was our shortcut of the derivative. If we went from x squared, we figured out our derivative was 2x, but in order to get that power rule, we had to use the limits to sort of figure that out. And then we did the same thing if I gave an equation like square root of x. Remember, we did the same thing. We did our limit, and we did root x plus h minus root x all over h, and then we rationalized and tried to solve it that way. And we did the same thing again if it was 1 over x or so on. So we basically figured out the power rule works for positive powers, negative powers, fraction powers, whatever, and that's what gave us the power rule. So what we're going to do today is we're going to figure out, can we do the same thing with... Okay, let's rewrite this on a new page. I got mixed up there a little bit. So let's clear this off and we'll start again. So if we start with our equation as sine x, the goal is, can we do the limit of sine x as h approaches 0, which would help us then figure out the derivatives. So it should work if we do the same sort of approach as we did before. So let's start with y equals sine x. So if we use our limit formula, we would do the limit as h approaches 0 of sine x plus h minus sine x all over h. So with regular numbers, we did rationalizing, we looked at doing foiling things out, we did common denominators, all of that sort of thing. With trig, the only thing we have at our disposal is trig identities. So in this case, what we do is use the sine x plus h identity. There's one on your formula sheet that's sine a plus b, and it's sine a cos a plus sine a cos b, plus cos a sine b. So that's the identity we're going to use for this question. So let's expand that out. So that would be sine x times cos h plus cos x sine h, and then we'd have minus our sine x still from the original part all over h. So that looks pretty good so far. So now our next step is, let's try to common factor out this sine x between these two terms. So let's rewrite it again as sine x in brackets cos h minus 1, and then our middle term would stay the same, cos x sine h, and all of that's over h. But I'm going to actually split it apart because we have two terms being added. Let's put h on this one, and let's put h on this one, and let's just treat this as two separate fractions being added together. So now you can see we have, back to our trig limits that we did yesterday, this cos h minus 1 over h will be 0. So the first fraction would be sine x times 0, which would just give us 0. For the second fraction, we have the same sort of thing, sine h over h, but that one's equal to 1. So the second fraction will be cos x times 1. So we end up just getting 0 plus cos x. So that means our derivative of sine is cosine. So there's our first derivative formula that we use. So it works really well. And I'll show you on the next page that I've got the notes that does the exact same thing we just did. So you can see the little formula thing, the limit formula, substitution, and then we got the same page where I got some room to write on it. Okay, so the next one we're going to do is cosine. So we already figured out the derivative of sine is cosine. So let's just move this over a little bit so we can see cosine. We can see that we could do the same thing. Cosine should be negative sine, or we know that cosine and sine are only off by 90 degrees using kind of unit circle. So we use the exact same thing. Let's do the limit that strategy. We get sine pi by 2 approaches 0. This time it'll be cosine and so on. So it works pretty good. Plus h. But let's actually minus cos x, and all of that would be over h. So now we can see we should be good to go again. Use our trig identity. But this time, though, the cosine identity is cosine x cosine h minus sine x sine h. The rest of it stays the same. And again, we're going to common factor out those two cos x's. So we should get cos x times cos h minus 1. Take away sine x sine h. All over h, and again let's split it into two fractions so we can see we get sort of the same scenario. We have cos h minus 1, which becomes 0, so that whole term is 0, and then we have sine h over h, which is 1. So you can see the only thing we have left over is negative sine x. So if our starting equation is cos x, our derivative ends up becoming negative sine. And that's really the only two derivatives we need to know. Tangents, we should be able to do the same thing. So let's try it. The nice part is with tangents or secants or cosecants, we don't actually need to do the limits anymore. We can just now apply our two derivatives that we do know. So if y equals sine x, our derivative was cos x, and if y was cos x, our derivative was negative sine x. So now all we have to do is apply what we already know to these new situations. So the next one I want to look at is what happens if we have tan x. So we don't need to come up with new limits, we just have to basically change it. So let's change our tan x using the sine divided by cosine identity. Now you can see we have sine divided by cosine. We know what the derivatives of each of those are. So let's try the quotient rule. So if our top is sine x, the derivative would be the derivative would be cosine on the bottom. And then for our second fraction, it's cos x on the bottom. The derivative of that is negative sine x. So now we can use our quotient rule formula. It'll be those two multiplied first. So cos squared, take away those two, so sine times negative sine, so we'll have negative sine squared, and the bottom g squared would be cos squared again. So that's our quotient rule formula. You can see that our minus minus would turn to plus, and we know from trig identities that's equal to 1. So 1 divided by cos squared would be our final answer, and if we want, we could rewrite that using an identity as secant squared. So on your formula sheet, if y equals tan squared, or tan x, our derivative becomes secant squared. So there's our first three primary trig ratios. We could do the same thing for secant or cosecant, so maybe let's just do one quick one. Let's try cotan would work the same, right? If I did cotan, it would just be cos over sine. So it works almost the exact same thing, except you'd get negative cosecant as your final answer. But let's try one more. Let's try secant. So we would change that to 1 over cos. And instead of doing quotient rule this time, let's try it as a chain rule. So let's write that as cos x to the negative 1. So now when we do our derivative and we follow chain rule, bring the negative 1 down, change it to cos x to the negative 2, times it by the derivative of the inside, which would be negative sine. So just normal chain rule should work. So in this case, our final answer should be negative 1 times negative sine would be positive sine. So we'd have sine over cos squared if we want to get rid of that negative power. And we could leave it like that, but to get the formula that's on your sheet, it gets simplified as sine over cos times 1 over cos. And sine over cos is the same thing as tan. And 1 over cos is the same thing as secant. So on your formula sheet, the derivative for secant should be tan times secant. And we could do almost the exact same thing for cosecant, and it works pretty much the same, except you would get cotan times cosecant, and it's negative as well. So we end up getting these as our 3 new secondary identities, and again, we can do the same, just change them to sines and cosines like we just did. So altogether we have 6 trig derivatives. So we went through sine and cosine using limits. We did tan using quotient rule. Cotan we could use quotient rule. Cosecant and secant we could do as chain rule, and those were the formulas we got. On your formula sheet, I give you these formulas slightly different. Instead of it just being sine x and derivative becomes cos x, the trig actually works sort of like a chain rule. So what happens is, if I give you an equation that's not just x, if I gave you something like sine of 3x, what we're doing is we're kind of using the chain rule idea. Let's just call that a u. So the derivative of sine u would be cosine of u, or in this case cosine of 3x. But because we have brackets, we got to get rid of that derivative of the u, so we have to times it by the derivative of the brackets. So in this case we would have to multiply it by 3. So every trig equation sort of follows a chain rule where we do the derivative of the trig part, so sine changes to cosine, brackets stay the same, but then you must multiply it by the derivative of the brackets. And it doesn't matter which trig equation you're using, that has to be the pattern. So let's go through a few examples, just so you can kind of get the hang of it. So this first one, we've got y equals cos negative 4x. So use your formula sheet. We would see that our derivative would be derivative of cosine is negative sine. Brackets stay the same. Now we have to multiply by the derivative of the brackets, which is negative 4. So we can just bring that to the front. The two negatives would cancel, and our final answer should be 4 sine negative 4x. So just remember to apply that chain rule idea to every trig equation that has the brackets. So the way I like to think about it is do the derivative of the trig part, then do the derivative of the brackets and multiply those two answers together. Okay, here's another one. Looks similar, just we got more junk in the brackets, but that shouldn't matter. So when you're doing your derivative, leave the 4 alone. Derivative of sine turns to cosine. Leave the brackets alone. And in this case, the derivative of the brackets is negative 4x. Derivative of 3 is 0, so we don't need to worry about that. So let's just bring that negative 4x out front. So our final answer would be negative 16 cosine of the brackets. And that's it. So most people, once you get the hang of trig derivatives, find them quite simple. Here's one where it's a quotient rule. So whether we're dealing with basic trig like the ones we just looked at, or you could have quotient rule, or chain rule, or product rule, all of the same principles still apply. So maybe we'll do a couple of each of those. So let's do this quotient rule one first. So let's call fx, or derivative of that would be 1. Let's call g sine x. Derivative of that would be cosine x. So now when we follow our quotient rule, it should be sine x times 1, take away x times cos x, all over sine x squared. And we can stop there. There's nothing wrong with that. We could leave it like that. If you wanted to, sometimes trig identities kind of help to simplify things. This case, maybe not so much, but let's try it. Let's write it as sine over sine squared minus x cos x over sine squared. So you can see in the first part, one of the signs cancel. So we just get 1 over sine. For the second part, we could actually split the sine up into 2. So we'd have cos over sine, which is cotan. And then we still have 1 over sine left over. So we could, you can see it's not really helping much, but we could change it. 1 over sine is cosecant. and then we'd have x cotan times cosecant as well. So you could leave it like that, would be fine. If we really wanted to be fancy, we could take out a cosecant as a common factor and have just 1 minus x cotan x. So all of these are acceptable. Generally for a test question, I'm not going to be too picky unless it'll simplify quite a bit. So I would stick with this yellow version. Is pretty good if you want to do your identities and change it so that it's just secants and cosecants and things like that. Then we could do the solution that we just did. Let's try one more. Let's do a quick product rule question. So let's try if I gave you something like x squared times tan x. So remember, we got to treat this as a product. We can't do any other little shortcut. So let's call f our x squared and g our tan x. So in this case, derivative of f would be 2x. Derivative of tan is secant squared. So now if we just do regular product rule, multiply those two, so 2x tan x would be our first one, and then we'd have plus x squared secant squared. And that would be good enough. There's no further simplifying necessary. I would just stop right there. Okay, let's look at a chain rule now. This one that's on the screen is a little bit tougher, so maybe let's do a different one first. Let's try a basic chain rule. So what would happen if I gave you something like cosine squared of 4x? So with chain rule, it probably works best to get rid of the trig notation for doing squareds. So what I would probably do in this case is rewrite this as cosine 4x in brackets squared, like that. So now you can see the chain rule should apply normally. Bring the 2 down, drop it to a 1. So that inside bracket stays the same. Now we got to multiply by the derivative of the brackets. So the brackets derivative of cosine is negative sine. Keep the 4x the same. But now we got to do the inside of that brackets as well. So remember, trig by itself is always sort of a chain rule. So just don't forget to do all the steps. So here, let's kind of go through it one more time. Bring the 2 down in front, drop it to a 1, then do the derivative of cosine, which turns to sine, negative sine, and then the derivative of 4x becomes 4. So just sort of work outside of the brackets and keep moving inwards. So our final answer in this case, we could rewrite it as negative 8 sine 4x and cos 4x. And we could stop there, or if you want, you could use the identity. There is an identity on your sheet for this case where you have, let me kind of rewrite it out here, where we have sine 2x equals 2 sine x cos x. So in this case, we could actually simplify this a little bit using the identity. Let's try it. So what I would do for this one is I'd rewrite it as negative 4 in outside, and then we'd have 2 sine 4x cos 4x. So now the brackets is following this pattern, so that would give us sine of 2 times our angle, which is 4x in this case, and we'd still have our negative 4 out front, so it's a little bit messed up, but it should work. We would basically be able to simplify that a little bit further to get negative 4 sine of 8x. So that would be an acceptable answer as well. So again, in terms of how far to simplify, you sort of have to use your common sense. And I would say in this case, it's the only reason I would probably go to that step is if I now asked you to do the second derivative. It's a lot easier to do what I did, the simplifying to do your second derivative, than it would be to do the product rule for the first answer. But they're both acceptable. Okay, let's try this first one that's on the page that we skipped over. And again, you can see it's kind of a chain rule inside of a chain rule. Where I would be careful with this one is I would write it as cosine of sine x. So in this case, sine is our angle. And then let's put our cubed on the outside. So now let's follow our steps again. Bring the 3 down, drop it to a 2. So that's our outside chain rule. So now we got to do the derivative of the sine part, or the cosine part on the inside. So that would be sine, negative sine of sine x. So that takes care of the outside cosine. Now we still have the inside brackets, and the derivative of that would be cos x. So it looks kind of messed up, but that's the way this one works. And all I would do is bring the negative out front, and we could rearrange it whatever order we want. Let's write it as negative 3 cos x. Then let's put the sine of sine x second, and then let's do the cos of sine x squared, and I'll just put the squared back on the inside. And that's it. So these are all being multiplied with each other, so there's nothing more we could do to combine those. Okay, one last one when we're dealing with secants and tangents and things like that. Just be careful when you're using your formula sheet. This one, the 12 stays the same. The issue is what happens with the secant. So on your formula sheet, the derivative of secant is secant, so the brackets stay the same, but it's also tangent. So we have to be careful and break the derivative into two parts. So the derivative of secant becomes secant times tan. The rest of it stays the same, but now we still have to take care of the derivative of our brackets, which in this case is a quarter. And we only do it once, even though the derivative had two brackets, we only go from the original. So derivative of 12 stays the same, derivative of secant becomes secant times tan, derivative of quarter x is a quarter. Now we can bring that quarter out front. So our final derivative should be 3 secant quarter x tan a quarter x. And that's far enough for this one. We don't need to do any other simplifying. So that's it for trig derivatives. You should be good to finish off the assignments. Watch for the simplifying. It's usually where the issue happens, and it's just basically using the identities to try to come up with a different way of writing your final answers. And that's it. We'll move on to implicit and second derivatives and all that kind of stuff in the next lesson.